Welcome back to Summarize Science. Today we're looking at a mind-bending idea, using the collision of dead stars to weigh one of the lightest, most mysterious particles in the universe. That particle is the neutrino, and for decades, its exact mass has been one of the biggest puzzles in physics. So, where can scientists find enough neutrinos to study in a controlled way? The answer lies in binary neutron-star mergers, some of the most energetic events in the cosmos. When two of these ultra-dense stars spiral into each other, they blast out both gravitational waves and a massive burst of neutrinos. The researchers analyzed how many neutrinos from these mergers we could realistically expect to see. Their updated calculations, using the latest data on how often these mergers occur, show a significant challenge. As you can see in this chart, even massive upcoming experiments like Hypercameo or HK will likely fall short of detecting even a single event over 20 years. The paper concludes that to catch these signals, we'll need to think bigger. Detectors on the megaton-scale, far larger than anything built today, will be necessary. But finding them is only half the battle. The real prize is measuring their mass, and that relies on a clever trick. Gravitational waves travel at the speed of light, but neutrinos, because they have a tiny amount of mass, must travel slightly slower. This creates a cosmic race. The gravitational wave signal arrives first, acting as a starting gun, and the neutrino arrives a moment later. By measuring this tiny time delay over hundreds of millions of light years, scientists can calculate the neutrino's mass. However, the analysis is complicated by the fact that the neutrinos aren't all released at the exact moment of the collision. This study presents a refined method that carefully accounts for this emission time, as well as background noise, to create a more realistic search strategy. And the potential payoff is enormous. These plots show the relationship between the measured time delay, the merger's distance, and the inferred neutrino mass. The results show that detecting just a single neutrino from a neutron-star merger could provide an upper limit on its mass that is significantly better than current terrestrial experiments. So, let's recap the key points. First, detecting neutrinos from neutron-star mergers is much harder than previously thought and will require enormous future detectors. Second, a realistic search needs to carefully account for both the travel time delay from the neutrino's mass and the emission time from the merger itself. But most importantly, if we succeed, this method offers a revolutionary way to weigh the ghost particle. While it may require decades of observation, this work shows that these cosmic collisions could be our best bet for finally solving one of physics' greatest mysteries.